Now let's try to solve or code the Fibonacci sequence using recursive functions or using recursion. I now have here the Fibonacci sequence. The first term is 0, the next term is 1, the third is 1, 2, 3, 5, 8, 13, 21, 34, and 55. So the Fibonacci sequence, the current term is the sum of the previous two terms. So for example, here, 5 is actually equal to the sum of the previous two terms, that's 3 and 2. This one, 8, is the sum of the previous terms, 5 and 3, and so on. So from this sequence, the first term is actually fib of 0. So fib of 0 is equal to 0. Next, fib of 1. So the next term is fib of 1. Fib of 1 is equal to 1. So the first two terms, we don't really have, by the definition, di ba? The current term is the sum of the previous two terms. So actually 0 here, there are no two terms. And at fib of 1, there are no two terms before it. Therefore, these two are our base cases. Now, fib of 2, we now have what? That is, we now have two terms before it. Therefore, we can actually compute for its value. And fib of 2 is actually equal to fib of 1, which is the previous term. And then fib of 0, which is the second term before it. Now, what is fib of 3? Fib of 3 is the sum of the previous two terms. So, this is fib of 3. This one is actually fib of 2 plus fib of 1. Okay? So you can see the pattern here. So as I have mentioned earlier, these are our base cases. So we have two base cases. So this is a base case. And this is also a base case. And what is our recursive case? So what is our recursive case? You can see here that fib of 2 is equal to fib of 1 plus fib of 0. Fib of 3 is equal to fib of 2 plus fib of 1. What is the relationship of this term or this value to these two values here, 1 and 0? So we can generalize that as fib of n is equal to the sum of the previous two terms. So what is the previous term of fib of n? That is fib of n minus 1. And then, two terms before it, it is fib of n minus 2. So now we have our base cases and we have our recursive case. Let's try to code this and see if it works. So again, I'm just going to put this as a comment. I'm not going to remove this for reference later. So I saved the file as Fibonacci.c. And of course, we need our preprocessor directive include stdio.h. Okay. And then we start creating our recursive function, and let's name it as fib. So it is int fib. It only accepts one parameter. So let's name that parameter n. Now we start off with our base cases. We have two base cases. Fib of 0. So this simply means that if the parameter passed is equal to 0, then we need to return 0. Fib of 1, if the parameter pass is equal to 1, we return 1. So how do we do that? So it's a simple if statement. If n, this one, is equal to 0, we simply return 0. Okay, else we have our another base case. If n is equal to 1, we return 1. Okay. Else, so if that's not the case, so we now have our two base cases here. We now go to our recursive case. So we return. So what's our recursive case? This one. So we just code that fib of n minus 1. So this part here plus fib of n minus 2. Okay? So the critical part in recursion is actually finding the recursive case as well as finding the base case. The base cases are important because those will terminate your recursive calls. If you don't have a base case, you will have an infinite loop. So let's try if we've done this correctly. So I'm going to create my main program. Return 0. And then let's ask for an integer. Printf. Please enter an integer. We need something to hold our integer. So let's declare n as an integer. And then scanf. %d n. I always forget the ampersand. So it's important that you put an ampersand. And then let's output. So I need a printf. Let's say fib of %d is %d. Let's put the \n. Our first %d is the integer inputted by the user, and that is n. And our next %d, this one, is the computation for the Fibonacci of that number. We just call fib of n. So let's try it. So I need to compile. Let me clear this first. So GCC Fibonacci.c. There's no error. And let's try ./a.out. Please enter an integer. Let's compute for the fib of 5. And fib of 5 is equal to 5. So let's check from our sequence. Fib of 0 is equal to 1. Fib of 1 is equal to 1. Fib of 2 is equal to 1. Fib of 3 is equal to 2. Fib of 4 is equal to 3. And fib of 5 is equal to 5. So according to our sequence, this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and the 10th term. So fib of 10 should be 55. So let's try that out. No need to recompile since we haven't changed our code. Let's just run the program again. If I put 10 here, then we should get 55. So it seems that our program is correct. So again, let's analyze what actually happened. So let's take the case of n is equal to 5. N is equal to 5. How did we arrive at the answer, which is, or fib of 5 is equal to 5? So let's trace our program. So once you input 5 here, you're going to call, or the program is going to call this function fib, and the parameter being passed is equal to, or n is equal to 5. So there will be a function call that is fib of 5. So we go here. Is n equal to 0? No, n is equal to 5. Therefore, this won't be performed. Else, if n is equal to 1, is n equal to 1? No, again, this won't be performed. So we will go to our recursive relation. So this will be performed instead. So fib of 5, when this is called, it will be actually be equal to fib of what? 4 plus, so 4 is n minus 1, 5 minus 1, and then fib of 3, right? So look, now we have two function calls here, fib of 4 and fib of 3. Therefore, we need to expand both function calls. Okay? So what is fib of 4? Fib of 4 is actually, again, we go back to this function. This time n is equal to 4. Is 4 equal to 0? No, this won't be performed. Is 4 equal to 1? This won't be performed. So this recurrence relation will again be performed. And fib of 4 is actually equal to fib of 3 plus fib. Okay, let me move this here. Fib of 2, right? How about fib of 3? Fib of 3 is equal to fib of 2 plus fib of 1, right? Now, you see this function calls here. This will all be performed. So let's further expand. So fib of 3 is actually equal to fib of 2 plus fib of 1. Or actually this part here. Again, let's move this for readability purposes. What is fib of 2? Fib of 2 is equal to fib of 1 plus fib of 0, right? Okay. So this one, fib of 2 here, can still be expanded. Fib of 2 here is equal to fib of 1 plus fib of 0. Okay. Now, this is already fib of 1. Can we further expand this? No, because 1 is a base case. So the 1 is actually what? This will be performed. Is fib of 0 expandable? Further expandable? No, because 0 is a base case. So once you reach a base case, your function call stops. So let's look at the final terms. This one, we can still further expand this. So let's say fib of 2. So what is fib of 2? Fib of 2 is actually equal to fib of 1 plus fib of 0. Okay. So let's try to move this. I think this is much better. Something like this. Okay, again, we started with fib of 5, and fib of 5 is actually equal to fib of 4 plus fib of 3. But what is fib of 4? Fib of 4 is equal to fib of 3 plus fib of 2, right? But what is fib of 3? Fib of 3 is equal to fib of 2 plus fib of 1. And what is fib of 2 equal to? It's equal to fib of 1 plus fib of 0. So every function call, we need to go deeper into that until we reach a base case. So what is fib of 3? Fib of 3 is equal to fib of 2 plus fib of 1. And fib of 2 is equal to fib of 1 plus fib of 0. So you see that it's like a tree. It branches out. There are several function calls until you reach a base case. So the recursion will stop once we reach all base cases. So what are our base cases? So starting from the bottom, we have fib of 1 plus fib of 0. This is a base case, fib of 1. This is another base case, fib of 1. This is fib of 0, another base case. So this is a base case, fib of 1, fib of 0, and then fib of 1. So if we bring that all down, what we really have is fib of 1. So this one plus fib of 0. This one plus this one here. Fib of 1 plus these two terms here, fib of 1 plus fib of 0 plus these two terms here plus fib of 1 plus fib of 0, and then lastly this one plus fib of 1. Okay, so these are the base cases that we arrived at. But what is fib of 1? Fib of 1 is equal to 1, right? And fib of 0 is equal to 0. So if we replace this as 1 plus fib of 0 is 0 plus fib of 1 is 1. Another fib of 1, that's 1. Plus fib of 0 is 0. Fib of 1 is 1. Fib of 0 is 0. And then lastly, fib of 1 is 1. So that is 1 plus 0 plus 1 plus 1 plus 0 plus 1 plus 1. So how many ones do we have? 1, 2, 3, 4, 5. And that's how we arrived at 5. So fib of 5 is equal to 5. So that's how recursion works. You start off by really tracing the recursive function. So we start with 5, and then we further go down the function calls until we reach the base cases. I hope this gives more a clearer explanation of how recursive functions works. Okay? Thanks, and see you in the next coding videos.